we have just spent an entire video being careful about signs in Faraday's law. And what we were doing was making sure that we defined our contour C and our integral dA correctly so we got a true equation. And that was all actually math. It was not physics. That was making sure we do the math right. So if we do our contour integral around the contour C in this direction, then when we do the integral of B dot dA, we should define our dA with a unit normal vector that points out at you, because I used the right-hand rule as we learned how to do. So that tells us how to relate the definition of this contour integral to this surface integral in the right way using our right hand so that we get a true equation. All good, but now I want to talk about this sign here, and this sign is physics, not math. So this minus sign here is physics, and here it is here. This is physics. And in fact, not only is this minus sign here physics, it is so important that it gets a name of its own. This minus sign in Faraday's law is itself referred to as Lenz's law, named after another pioneer of electromagnetism named Lenz. So what's the physics of this minus sign? So getting the relative sign of the sides right, that was math. But now what's the physics in this minus sign? Well, the easiest way to explain that is with an example. Let's use the example that we've used before of a magnet, which I'm moving the magnet into a loop of wire. So I have this bar magnet. I'm moving it into the loop of wire. That's increasing the flux through that loop. And if I apply Faraday's law with this minus sign, I conclude that I induce an EMF in that loop, which drives the current in the direction shown. Now, this minus sign tells me the direction of this current. If I had a plus sign here, the current would flow the other way. Okay, that doesn't sound so important. It tells me the direction of a current. But the direction of this current tells me that when I think about now this loop of wire with a current flowing through it, that loop of wire with a current flowing through it, that current makes a magnetic field of its own. And the direction of the current tells me that the magnetic field created by this loop of wire, which is now carrying a current, has its north pole on the left side. Why is that important? Well, that's important because I now have a north pole fighting against the north pole. So as I am pushing this magnet towards the loop, that the flux increases through the loop. It induces a current through the loop. And that current flows in a direction such that the loop itself becomes a magnet with a north pole that fights against the north pole coming into it and pushes back. And so Lenz's law, in words, is the statement that the induced EMF in the loop, induced according to Faraday's law of induction, is always in the direction so as to oppose the change in flux. So the induced EMF is always in a direction so as to oppose the change in flux that caused it. That is Lenz's law in words. And Lenz's law in equations is the statement that, hey, there's a minus sign here. So this is responsible for what we saw in this demonstration, which I did previously for you in the lecture theater, and now I'm just going to redo it here. When I take this magnet and I drop it through this copper pipe, it goes very, very slowly. Let's just remember. Well, first of all, let's just remember how magnets fall when there's no copper pipe. So here's this magnet, and I'm going to drop it. That's the acceleration due to gravity on the magnet. But now, let's do it in the copper pipe. So I drop it into the copper pipe, and I wait, I wait, I wait, I wait, I wait, I wait. Where is it? Where is it? Where is it? There it is. It finally came through. I'll do it one more time. I drop this magnet through the copper pipe, and I wait and 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 wait. And there it is. Now, how is that related to this minus sign? Well, as this magnet is falling through the pipe, you can think of every little bit every little cross section of the copper pipe just below the magnet as a loop, like in this example here. So think of a cross section of the pipe right here, and this magnet is heading towards it. There's going to be a current induced in this loop of copper right there that's going to make this loop of copper create a magnetic field whose north pole is going to be fighting against the north pole of the magnet coming into it. And so gravity is pulling this magnet down, but the north against north magnetic repulsion, the repulsion of the north pole from the magnetic field induced by the current flowing through the loop of copper here, fights against the north pole, pushes against the north pole of this magnet and holds it up, slows it down so it falls through the pipe more slowly. So this minus sign is responsible for what we saw when we did this demo. If this had been a plus sign, when I dropped the magnet in the pipe, it would have accelerated faster than gravity because there would have been the current would have been in the opposite direction. It would have been trying to suck the magnet downwards, and the magnet would have been pulled down by both gravity and magnetic forces, and it would have fallen faster. The fact that the magnet falls more slowly means that there's a force opposing what the force of gravity is pulling it down, but there's a force opposing its motion, and that comes from this minus sign in Lenz's law. The other demo that we did that this should remind you of is the one where I had a loop of wire and I shot a magnet through it. And if you remember, when the magnet was going into the loop, the current flowed one way. We saw that with that needle on the meter tipping one way. And then as I pulled the magnet out, the current flowed the opposite way. So let's think about that for a minute. Let's imagine here that I've taken this magnet and I've moved it all the way. Actually, let me go back to this picture. And let me imagine now that I've taken this magnet and I've moved it all the way through, and I've got the magnet over here now, and I'm pulling it this way, pulling it out. Now, as I'm pulling it out, the flux through the loop is getting less. Flux was getting more. Now the flux is getting less. That means the sign of d phi by dt changes. Okay? And because the sign of d phi by dt changes, the sign of the current changes. And that means that the current is going to go the other way. The magnetic field is going to have the other sign. The induced magnetic field is going to have the other sign. And it's going to have a north on the right now instead of a north on the left like before. And that means that when I'm pulling the magnet out this way, the coil generates a magnetic field that tries to pull me back. So let's come back to our copper pipe here. And now we have the whole story, actually. So let's imagine this magnet right about here, falling through the pipe, right about here at this height. And now, if you think about this loop of copper just above it, there's a current induced in this loop of copper that makes a magnetic field that tries to pull the magnet back up. And if you think of this loop of copper just below it, there's a current induced in this loop of copper that tries to push the magnet upwards. So this loop, there's a current that pushes that way. This loop, there's a current that pulls that way. And the net result is the magnet falls very slowly, and I'll do it one last time. I have to get ready to catch it. There it is. Here it comes, here it comes, here it comes, here it comes. Took a while, and finally there it is. So this minus sign is responsible for the very basic features that we've seen in this demonstration with the copper pipe and in what we saw when we were throwing the magnet back and forth through the loop of wire. And this minus sign has a name. It's called Lenz's law. And in words, it's the statement that the EMF fights against the change in flux that's inducing the EMF. And that is Lenz's law in a nutshell.